part B.2, Introduction to Heapsort. So in this video, the first, we want to look at why we need to study this new sorting algorithm. The first question. All right. So we look at a sort problem, our original sort and array problem, number 4. So we try to use another solution. Why we have so many different sorting algorithms, why we need another one? Yeah, for some special reason. There is some special requirements we like to have sometimes for some real-world applications. Here, what kind of special requirements do we need? Yeah. So let me give you that part first. These special requirements. First, worst case efficiency should be in this big theta of n log n. So you can see this requirement will eliminate quicksort. Quicksort is not in this category. Eliminate it. Okay? Insertion sort can be eliminated. All right? So only the merge sort satisfies this requirement. Merge sort has this property. Okay? All right. So let's look at our second requirement, in place. You know the meaning of in place, right? Yeah. So the extra storage space used, big theta of 1. Okay? So for the in place requirement, so you can see the merge sort is not in this category. The merge sort. Merge sort, we need to use a lot of extra space. Okay, yeah. Number 3, maintain dynamic data efficiently. This is a new requirement. Dynamic data efficiently. What do you mean, dynamic data? Yeah. Data keeps coming in. Yeah. So when you run your application, so we know when we run this program, so there is a period. Yeah. New data keeps coming in. Yeah. And you need to maintain your dynamic data. The maintenance step, is that very expensive? So we want some efficient way to manage the dynamic data. So this is another important requirement. Yeah. So with these 3 requirements, do we have any existing sorting algorithm that satisfies this condition? No, we don't have any. So for that reason, we need to develop a new sorting algorithm, Heapsort. Heapsort will solve this problem in a, perfect way. Yeah. Yeah. In a very nice way. Yeah. All right. Yeah. What's the meaning efficiently, right? How fast do you treat it as efficient? Yeah. Here we can use the insertion sort to give us idea. For the insertion sort, every time when you insert new data into the current ordered array, you need big theta of n, that much cost. And we do not treat that cost is efficient. It is pretty slow. So we feel that is very slow. So we don't like that way. So we want a much better way than that. Okay? So then I will go big theta of log of n. Log of n. Yeah. We target this efficiency. That's our goal. Yeah. All right. Idea. How can you do it? Idea. Yeah. First, for this one, you can see this problem is not easy to solve, not quite easy to solve, right? Yeah. So first, we need a new data structure. Usually for some relatively advanced algorithm, you need some advanced data structure. Here we have that situation. We need to start with a new data structure. Yeah. So it is a binary tree structure. Why binary tree? Binary tree, we know the height of a binary tree, that's the log of n. Okay? How can you get log of n? Efficiency, right? Yeah. So that's connected. If you can organize your data in a binary tree structure, then you have a good chance to get logarithm efficiency. That's the reason. Okay? All right, so next, design of data structure. How do we design our data structure? Yeah. First, when we design it, we want to make it as simple as possible. We don't want to choose a very complicated data structure. The implementation cost is extremely high, not worth it, right? Yeah. So first, we want to choose some relatively simple existing data structures. Yeah. So let's look at our candidates. Now, the data structures we have learned before. Okay, yeah. Array is one, yeah. Most frequently used data structure in our experience, array. Yeah. So definitely our first candidate is array. Second one, linked list. Another data structure, we rarely use it. We rarely use linked list. Yeah. For this class, we haven't used it, right? Linked list. You learn this data structure in 20 to 50, the data structure class. Yeah. All right. Yeah. Here, we take a look. Yeah. But we know it is much more complicated than array, right? Yeah. Much more complicated than array. Yeah. All right. So array is a simpler data structure. The question is, can we use array, right? Can we use array to help us organize our data that satisfy all the requirements? Yeah. We need to look at that first. Yeah. The question, can we use an array directly? So without doing anything, just use array directly. That may be hard. So let's see what's the problem if we use an array directly. We need to consider the main part, main feature. We need maintain dynamic data. Maintain dynamic data. This part, how easy we just use an array directly. Yeah. Especially, we want very efficient way. Efficient way, we mean big theta of log n. That efficient. Right now, we don't have any idea on it. We cannot. Okay? So the answer is no, we cannot do it. We cannot insert a new coming data into an ordered array in big theta of log n efficiency. We cannot do. Okay? Yeah. Based on our current knowledge. Okay? All right. Discard it. Should we discard it and look at a linked list? We know the linked list is very complicated. Okay? If that is the only way we can try, we have to look at it. Yeah. But should we discard the array immediately at this point? Yeah. So wait a minute. Hold a little bit. Yeah. Probably we can save it, right? Yeah. Probably if we can do a little more to fix the problem, then we can save this nice data structure. We like its simplicity. We like its simplicity, but we just want it to have some extra feature. Support the dynamic data efficiently. That's the thing we need. We don't have it at this point. The question is, can we do some extra work to add that feature into the array? If we can do it, we will have a perfect candidate. We'll have a perfect candidate. All right. The question, can we modify to make it work? Yeah. So let's try it. Let's try it. Okay. Yeah. All right. So the next question, next step. Now, the goal, our new goal, build the binary tree structure in an array. So this time we need to do something useful here. Build a binary tree structure in an array. Our new goal, yeah. How to do it? Yeah. So how to modify the array to store a binary tree structure in a given array. So that's an interesting question. Okay, all right. So let's look at our current situation. We store data in an array. At the beginning, we can sort the data. Yeah. At the beginning, the first time we want to get our data sorted, to organize the data. Yeah. But the question is, we will have new data items keep coming in. Okay, yeah. So we need to add new data items into the current ordered array. Yeah. So when a new data item comes in, directly the data is not in order. So we need to fix it. We need to make the new data ordered. Yeah. How to make it in order? So how efficient you can make the new data in order? That's the most important question we want to ask here. Yeah. Insertion. Let's look at insertion operation, because that's an insertion operation, right? Yeah. But for the insertion, our current insertion, in our insertion sort, we did that in our insertion sort. That's the big theta of n. We don't like it. Too slow. Yeah. So we drop this idea. Yeah. Our target, we want to get the logarithm efficiency. Big theta of log n. And we know the binary tree structure can help us to get that. If we organize our data in a binary tree structure, then we have a chance from the top to the bottom, from the root to the bottom level, that's the height corresponds to log of n. Okay? So we will take that. If that's possible, we will take that solution. Yeah. All right. So next, let's look at the solution, insertion part. Regarding the insertion, based on our experience, we have two different types of insertion. Two different types. Yeah. The first type is linear search. Remember, yeah, from the last to the first, one by one. That's based on the linear search. We don't like that. That's the, big theta of n efficiency. But the second one, we use that. Before the second one, yeah, I gave you a few examples. The second one, yeah, sorting 5-element array. So if you still remember, sorting 5-element array at the end of the insertion sort. So if you want to go back, refresh your memory, sorting 5-element array, we use the binary search based insertion. Okay, much better, much faster. And we know the binary search that corresponds to the binary tree that will give us big theta of log m efficiency. So we like that idea. Okay, Then another thing, no shifting operation. No shifting, because in our linear search, after we find the location, we need to do a lot of shifting operation, right? We need to do that big theta of n shifting operation. All right, so that is very expensive. So in our new way, we organize, we do the binary search based insertion. We definitely need to do some adjustment. Definitely we need to do some elements arrangement. We need to pay some cost, but the cost we need to pay this much. We don't want to pay that much cost. So that's why I say no shifting. Because when you do shifting, it is very likely you get big theta of n cost. That's too expensive. All right. Next question. How to get it? How to get it? Okay. So our next video, we will look at how do we build a binary tree structure in an array. If we can do that, then we can get our goal. So let's complete the first video. That